Well, I never thought that.
It also helps when it says like, oh, you have
No, they don't tell me that. It's gonna say like 2+ hours.
it promise you all this. I don't know.
So last class, we talked about how to find local minimums, maximums, or saddle points. And today we're going to move on to the second topic. There are 3 topics in optimization: local minimums and maximums, absolute minimums and maximums, and Lagrange multipliers. So today we're going to talk about absolute min and max. Okay, so when we go about looking for absolute minimums and maximums, we need a domain in the XY plane. So if here's your x-axis and here's your y-axis, maybe it's a circle. So this will be your domain D. And then we have some function f of xy, let's say is equal to x squared plus y squared. And we can then ask, what are the absolute minimums and maximums of this function? Of f in the domain, in D. So we're not going to ask for the absolute minimums and maximums over the entire space. But we will ask what are the minimums and the maximums, the absolute ones of f contained in some domain. And this is kind of similar to what we were doing in Calc 1, where we have some one-dimensional function, so x, y, and here's your function, f of x. And when we tried to find the absolute minimums and maximums, we said, okay, in this interval, what are the minimums and the maximums? And in this case, because it's always increasing, it will be this point here. So we'll use a similar strategy with D. We want to find the critical points of f in D. So let's say some points over here. But we also have to pay attention to the boundary. If you remember from Calc 1, in the one-dimensional case, you look for the critical points in your domain of your function, but then you also plug in the boundary points because they might be the absolute minimum or maximum. So we do the same thing here. We look for the critical points in the domain, and then we look for the critical points on the boundary. So we might as well do this problem. So let's imagine that our circle, so our D, is given in the form, let's say R of t is equal to cosine of t, sine of t. So this is a circle with radius 1 and 0. Let's imagine that that is our domain. So how do we find the absolute minimum and maximums of f in this domain, right? We know how to find the local minimums and maximums or saddle points, but how do we find the absolute ones? So what we are going to do is first we find the critical points of f. And the strategy for that is the same as the beginning of the strategy for the from the previous lecture, which is to take the gradient of f and set it equal to 0. So this tells us that the partial of f with respect to x, which is equal to 2x, should be 0. And the partial of f with respect to y, which is equal to 2y, should also be 0. And that tells us the critical points inside the domain, which of course is the point x is equal to 0, and y is equal to 0. So 0, 0 is a critical point, right? And why is that? Well, this is a parabola. It goes upwards, so it looks something like this. And so 0, 0 is, of course, a critical point and happens to be the absolute minimum. But we don't necessarily know that yet. We know it's a critical point. So we write, okay, 0, 0 is a critical point. What's next? So the second thing that we want to do is we want to turn this function into some one-dimensional function at the boundary. So at this, because we need to now look for the critical points at the boundary as well, right? The same way that in the one-dimensional point case we just plugged in the boundary. In this case, we need to actually look for the critical points on the boundary. So how can we do that? Well, we can say that on my boundary, this is what the curve I get, right? And so what is my function going to be on the boundary? Well, I can take this curve and I can plug it into my f of x, y. So let's do that. So again, f of x, y is equal to x squared plus y squared. And my curve r of t is equal to cosine of t, sine of t, and 0. So plugging that in on the boundary, we get f of, let's say, cosine of t, sine of t, which is equal to cosine of t squared plus sine of t squared. And we know that this is equal to 1. So we can say that on the boundary, all the points are the same, right? And that makes sense. They're all some curve like this, where all your points are just 1. So that would be the entire thing is your absolute maximum. All the points on the boundary give you your absolute maximum, which is f of x, y is equal to 1. Any questions about this? Yeah.
For the boundary, why was the z equal to 0?
So because we're in the domain, so we're only looking at the domain. This is our domain. So our z is equal to 0. On the domain, your f, so your domain is down here. But what is your f on the domain? What's the function on the boundary of your domain right over here? Well, that's this over here.
So f is 0.
No, f and z are the same. So on the domain over here, you would have the curve cosine of t, sine of t, 1. That's over here. But on the domain, you don't have that. You have cosine of t, sine of t, and 0. So that's your domain below at the xy plane. So z is 0, right? And that's the question. What is the maximum of your f on this domain? What's the max? And it's 1, right? It's the same for all functions, for all points. And so the maximum is 1. So now we can say 0, 0 is our absolute min. And the curve, the entire curve, cosine of t, sine of t, 0 is our max. Those are all our maximum points. And our min itself is f of 0, 0, which is 0. And our max itself is f of cosine of t, sine of t, and 0, which is, of course, 1. Any questions about this? Yeah.
Do you go over to where you found?
So you're given the domain, and then you first find the critical points in the interior, and then you plug in your domain and you start searching for the critical points on your domain. It happens to be that my function is constant on my domain. So it's like, what are the critical points, right? This is a one-dimensional function right now, only in terms of t. So let's imagine my t is here, and now my f is here. And I told you that my function is 1. What are my critical points? Well, they're all my critical points, right? They're all maximums or minimums, right? So that's why on this domain, on the boundary of the domain, all the points are critical points, and all the values of those critical points are 1. So let's do a slightly harder twist to this problem, which is instead of looking at the circle where all the points are the same, let's instead look at the same function. So again, f of xy is equal to x squared plus y squared. And now let's say that my r of t, well, my domain, so my domain is, again, not going to be a circle, but rather it's going to be some ellipse. And let's say that in this direction, it has, some radius, and in this direction, it has some other radius. Okay? So this is my domain right over here. And let's imagine that the boundary of the domain is given in the form r of t is equal to, okay, so the second one will just be sine of t. And the first one, let's say, is let's say 1/2 cosine of t. Okay? Does this make sense so far? So let's imagine that this is the curve that gives this boundary. It's giving this boundary right over here. And of course, when t is 0, your sine is 0. So you get 1/2 cosine of t. This is the point over here. 1/2 cosine t. And if we plug it in, squared. And what is that going to be equal to? So 1/4 cosine, okay, cosine t is 1. So 1/4 times 1. Okay, and that's what this will be. So maybe this should be 2 if we want it to be bigger, but it doesn't matter. Okay, so let's imagine that I'll just put 2 here. Doesn't really matter. Okay, yeah, so if you plug these into here at t being 0, the y component is 0, the x component is now 4 cosine of t squared, and that's going to be equal to 1 at 0. So it's 4. So that's your x component now. Okay, any questions? So what do we do now? So the first part of the strategy is just the same thing. We have this function inside of this domain. Let's find its critical points in the domain. So that's the gradient of f again is equal to 0, which means that 2x is equal to 0 and 2y is equal to 0, which means again you have the critical point 0, 0. So once again, and this makes sense, of course, this point is the point 0, 0. But now, when trying to figure out the critical points on the boundary, so let's first draw this graph, the parabola. So now here's your parabola. This is your x, this is your y. So now your domain looks something like this. So the type of curve that it carves out now looks something like Maybe it would still, let me see. Yeah, maybe it looks something like this. Yeah. It kind of goes down and then comes back up, right? It looks something like you know, yeah.
You say the gradient of f is equal to 0, that means the gradient of f at 0 is equal to 0?
No, you're looking for the points where the gradient is 0. So the points where this function is flat. So you take, 2x comma 2y, set that equal to a 0, 0, and solve. Any other questions? Okay, so now in order to find the second part of this problem, we plug our function in to figure out what this function is on the boundary. So that would be f of 2 cosine of t sine of t, which is equal to 4 cosine of t squared plus sine of t squared, right? That's our curve currently. That is this curve right over here, this purple curve, which is what your function looks as you go along the boundary down here. As you go along this ellipse, you get this curve up here. Something like that. And this is how that curve looks. So we want to find the minimum and the maximum on this curve. So we want to, this is a one-dimensional curve, and we would like to find the critical points of this curve. So how do we do that? Well, take this new f prime of 2 cosine of t sine of t, and set it equal to 0, like any Calc 1 problem, right? Because we can think about this now as being a one-dimensional curve, and we can try to find the maximum and the minimum of this curve. So what happens if we take this derivative and we set it equal to 0? So we get 4 cosine of t, sorry. We get 8, okay, we're setting this equal to 0, 8 cosine of t negative sine of t plus 2 sine of t cosine of t is equal to 0. So what does this tell us? It tells us that negative 8 cosine and sine, so it's negative 8 plus 2, so negative 6, and we can get rid of the negative because there's a 0 here. So 6 cosine of t sine of t should be equal to 0. So far, so good? We can get rid of the 6 now, and that tells us the cosine of t sine of t is equal to 0. So we need either cosine or sine to be 0, and we get our critical points. So where are our critical points? Well, there are these 4 points over here. This point over here, right? At this point, cosine is 0, sine is 1, so we get 0. This point over here, at that point, sine is 0, cosine is negative 1. This point over here, at this point, sine is negative 1 and cosine is 0. And this point here, where cosine is 1 and sine is 0. Those are the 4 points that make this equal to 0. And that makes sense. These points, this point corresponds to some maximum. This point also corresponds to some maximum. These points correspond to these 2 minimums. Does that make sense? Any questions? So now we have a list of all our critical points. We have the point 0, 0. we have this point over here, which is going to be the point 1, 0. We have this point, which is going to be the point 0, 1. We have the point -1, 0, and the point 0, -1. These are all our critical points. Now, I know you can now start plugging them into your function to figure out what are your absolute minimums and maximums. Once you get a list of your critical points, both in the interior of the domain and on the boundary of the domain, you plug them into your function to figure out which are the biggest, the lowest, and the highest values. So again, our function is f of xy is equal to x squared plus y squared. So let's plug in. F of 0, 0 is equal to 0. Yeah.
Can you explain why it's 1 on the x-axis, not 4?
Oh, yeah, it would be that. Yeah, so this point over here is going to be the point 4, 4, 0. Then the next one is the point 0, 1, -4, 0, and the point 0, -1. Yep. Okay, any other questions? Okay, so now we can start plugging in 0, 0, we get 0. F of 4, 0 gives us 16. F of 0, 1 gives us 1. F of -4, 0 also gives us 16.
No.
And f of 0, -1 gives us 1. So what are the lowest points here? This one is the lowest point here. This point over here is the lowest point. So it's the absolute min. What are the maxes here? This point over here, 16, and this point over here, 16. These are the maximums. Which again makes sense. If we look at this, where is our minimum? It's here. Or maybe I should. Here's our minimum. And here are our maximums, right? The other two critical points are not as low as this minimum, right? This point and this point are not as low as our minimum and not as high as our maximum. So we have two absolute maximums and one absolute minimum. Any questions about this? Okay, and that's in general, I would recommend remembering this problem because the entire strategy lies in this problem. Figuring out the critical points in the interior, figuring out the critical points on the boundary, plugging all the points in. So let's try another problem.
We have a quiz on Friday, and this is what it's going to be on.
Yeah, we're gonna have a quiz on Friday. It's gonna be about the stuff that we did yesterday. So local minimums and maximums, saddle points, the equation D, right? So you have to know how to use the equation D. Xy is equal fxx, fyy minus fxy squared. So I have to know how to use this equation. And then the stuff that we're doing today, which are absolute minimums and maximums. And then what we're doing tomorrow, which is going to be Lagrangians. Okay, so let's try another problem here. So they ask us to find the absolute min. So find and max of the function f of xy is equal to x squared plus 4y squared minus 2x squared y plus 4. On the rectangle, so on the domain, so here's my domain D, which will be given by, so the rectangle, which is given by the x being bounded by -1 x1 and y being bounded by -1 y1. In my experience, this stuff is absolute minimums and maximums are harder for students than local minimums and maximums, especially when it comes to the boundaries. Everyone some people have a problem with the boundaries. So I would recommend to try to understand what's going on. It's not, crazy complicated, and to draw a lot of pictures. So let's draw our first picture, which is our domain. Where are we trying to find the absolute minimums and maximums? So it's here's my x, here's my y, and it's in a rectangle where my x goes from -1 to 1. So here's -1 and here's 1. And my y goes from -1. So here's my -1 and here's my 1. So it's this rectangle right over here. Yeah, this is my domain. So this is D. Yeah.
Did the problem tell you it was a rectangle? Or you just know from the formula?
The problem told the problem did tell me it's a rectangle, but you can just look at the boundaries and go, if my x is going from -1 to 1, then I know where my x is going from where to where. And if my y is going from -1 to 1, I know that too. So you can, without knowing it's a rectangle, you can draw it and see, oh, this is a rectangle or a square or whatever. And later on, especially when we're taking integrals, this needs to become like a second habit of being able to draw a picture of a domain. So it's good to get practice with that. Okay, so now step one, the first step is to find the critical points in the interior. So all of these critical points. Can anyone tell me what I do in order to find these critical points? Yep.
On the gradient.
Yep, set the gradient to 0. So gradient of x, y is equal to 0. So what does that give me? It gives me, well, we're taking the partials, 2x minus 4 x, y is equal to 0, and 8y minus 2x squared is also equal to 0. So far, so good? Okay, so what's the next step? So we need to try to figure out what values x and y make this system of equations equal to 0. So of course the value x is equal to 0, y is equal to 0 works, right? If my x is 0 and my y is 0 here, I get 0 and 0. So I can, but let's do it step by step. So let's take the first function and rewrite it. So we get 2x is equal to 4xy. I can cancel the 2 and the 4. So I get x is equal to 2xy. Now, don't just have the habit of dividing by the x. The x might be 0. So we have a case now. Either x is equal to 0, or we can divide by x, and we get that 1 is equal to 2y, which tells me that y is equal to 1/2. Okay, let's go case by case now. If my x is equal to 0, using my second equation, I can plug in x is equal to 0 into my second equation, and I get 8y is equal to 0. So that tells me y is equal to 0. So that's the first thing that we got. We knew that the point 0, 0 is a critical point. Okay, and now we have it. Our first critical point is 0, 0. Okay, what about if y is equal to 1/2? So again, plug it into the second equation, and we get 4 minus 2x squared is equal to 0, which tells us that 4 is equal to 2x squared, which tells us that 2 is equal to x squared, which tells us that x is equal to plus or minus the square root of 2. So we now have the following critical points. We have the point 0, 0. We have the point 1/2. Sorry. We have the point square root of 2, 1/2. We have another point, negative square root of 2, 1/2. Yep. Okay, any questions about this so far? These are our first 3 critical points. So they are in the interior. We now know this is a critical point, and there are 2 other ones. So whatever they are, I mean, this actually kind of works. Okay. Second step. So we need to remember our critical points. You can make a little list of them. I will eventually just put them in a list. But for now, let's start working on the boundaries. So because we have these type of boundaries, we need to consider 4 different boundaries. This boundary right over here, this one, and this one. So let's call them names. D1, D2, D3, and D4. So let's start working on the D1 boundary. D1. So in D1, we have that x is bounded. So x varies between -1 and 1. So we can write that x is bigger than -1 and x is less than 1. And y, so what is y on this boundary? Yeah, y is equal to -1. So once we know this, we can plug that into our equation and get a function only in terms of x. So a one-dimensional function, which makes sense. On this part of the boundary, our function is one-dimensional. It's only a function with respect to x. Y is not varying. So plugging that in, we get now that my f of x, -1, because my y now is fixed at -1, is going to be equal to x squared plus 4 minus, so plus, because y is -1, 2x squared plus 4. This is equal to 3x squared plus 8. Any questions about that? Okay, perfect. So now we need to find the critical points on this part of the boundary. So what do we do? Anyone? Yep. And set it equal to 0. So f prime of x -1 is equal to 6x plus 8. And we set this equal to 0. So that tells us that 6x is equal to -8, or x is equal to -8 over 6. Yep, that seems right. Yep. So again, taking the derivative, we got 6x is equal to 0, x is equal to 0. So what is the critical point? Can anyone tell me the exact critical point that we just found? Yes?
0, -1.
Yeah, 0 for our x direction, -1 for our y direction, because we already know that y is -1, yeah? So we're doing what you do in Calc 1 when you want to find critical points of a one-dimensional function. So this is a one-dimensional function. It's a function only in terms of x. It's a function that tells you how your original function looks on this line, right? So your y is fixed and it varies in terms of x. We want to find the critical points of that function. So what do we do in order to find the critical points of that function? We take the derivative and set it equal to 0, which is what we did. And then we get what our x is. We already knew what our y was. It was -1. And so we get a new critical point, 0, -1. So let me write that in our list. 0, -1. New critical point. Yeah.
What is that critical point?
Nothing yet. You're going to have to plug all of these critical points into your original function. And then you get a list of numbers. The lowest ones are the absolute minimums, and the highest ones are the absolute maximums. Yeah.
Why don't you check that one of the critical points is a max?
Because you can have, so the same way in Calc 1, let's say you have a function that just goes up. And then here's your boundary. Where's your critical points? It's on the boundary. It's this point right over here. That's your absolute maximum, and this point is your absolute minimum. So just knowing what's going on in the boundary will not be enough to tell you the total amount of information. You also need to know what's going on the boundary, right? You can imagine that the function goes up and up and up, like a parabola, right? For the parabola case that we did, right? Where was the absolute maximum? It wasn't given in the interior, it was on the boundary. It was this point right over here, at this point. So you have to check the boundary. Because even if it might not be a critical point with respect to the function, it might be a critical point with respect to the function if you cut it at the boundary, if you stop thinking about the function at the boundary. Does that make sense?
You have to do that even if you use the D formula to know that the maximum inside.
So the D formula just tells you that it's a local minimum or maximum. The D formula is a formula only with respect to derivatives. It's a local piece of information. In a little piece of, is this a minimum or a maximum? But it doesn't tell you if it's an absolute minimum or maximum. And if your function is on the entire domain, the XY plane, just looking at where the derivatives are 0, where the gradient is 0, will not be enough to tell you if it might just go to infinity. So you're not going to know if you have a minimum or maximum. So you have to have it in a boundary. You have to check the critical points in that boundary. And then you just make a list and you plug it into your function, and whatever points are the lowest, right? Like we did here, you plug, these were our critical points right over here. And we plug them into our formula. And the lowest one, that was our minimum. And the highest one, those were our maximum. So that's what you do every time. Yeah.
You're always going to get the domain.
Yes.
It'll always be there.
Yes. Yep. Any other questions? Okay, so let me just check this.
I got a quick question.
Yep.
Can you go back down to the example we just did?
Well, we're not done yet, by the way. We have to do this part, this side, and this side. We know of one critical point here, 2 here, and now 1 over here, right?
When I asked, like, to get to the
Yes. Yep. Yeah. I'm just trying to make sure that whatever it is that we got for now is correct. Okay, looks good. So next part, D2. Okay, D2. So on D2, our y is varying. So y is between -1 is less than or equal to y is less than or equal to 1. And our x is fixed at 1. So x is equal to 1. So going to our function, our original function was f of xy is equal to x squared plus 4y squared minus 2x squared y plus 4. So what is f? Now my x is fixed at 1 y, right? That's my new function, now only changing with respect to y. So that's going to be equal to 1 plus 4y squared minus 2y plus 4. Any questions so far? Okay. So what is this equal to? It's equal to 4y squared minus 2y plus 5. That's my current function. Let me just check. Okay, perfect. So now we take the derivative and set it equal to 0. So f prime of 1y, well, that's going to be 8y minus 2. And we want to set this equal to 0. So that's 8y is equal to 2, which tells us that y is equal to 1/4. So we're given another critical point, 1/4. Does that make sense? Okay. Now I want to just, mention something that's going to help, which is that our x are squared. So the same thing would work if you put a -1 here. You would get the same exact formula. And you would therefore also have a critical point when x is -1 and y is 1/4. So we can kind of skip the D4 case when x is -1. Well, we're getting the same thing, but now x is just -1 because the x's are squared. Any questions about this? Okay, so now for the last case, the D3 case. So we can skip the D4 case, the D3 case. Please take 2 or 3 minutes and do the D3 case. Now I'm going to add to our list our new points. -1 1/4 and 1 1/4. Sorry, what? Because this function, the x's are squared. So when x is 1 or -1, it doesn't matter. So you get the same function, right? If you put a -1 here instead, same function. But when it comes to your critical point, you just have to remember that your x was now -1. Okay, so we got one critical point somewhere here. I don't know, maybe here, and another one here. And now we just need to figure out what's our critical point in the D3 case. And that's up to you guys. Anyone who figures it out, if you can just tell me, that would help. Zero, one. Okay, 0, 1. Okay, so last step, plugging it into our f of xy. And generally, my guess is on the exam, things won't be this complicated. You have to now take each one of these points and plug it in and see what you get. And I'm not going to do that, but I'll tell you what they tell me it is, just so that we can see the next step. So f of 0, 0 is equal to 4. F of 1, 1/4 is equal to 4.75. Okay. F of -1, 1/4 is equal to 4.75. F of 1, -1 is equal to 11. So yeah, you have to do this with all the points. F of -1, 1 is equal to 7. F of 0, 1 is equal to 8. F of 1, 1 is equal to 7. F of -1, -1 is equal to 11. And F of 0, -1 is equal to 8. So what are our absolute maximums? Anyone? So yeah, -1, -1. I mean, sorry, 1, -1. So this is a maximum right here, where f is equal to 11. And this is a maximum. And then this over here is a minimum. And that's it for today. And I'll see you tomorrow. Yeah?
When we get the 1, -1,
The 1, -1, this one?
when we get the, when do we get the? Yeah. Or the -1 and 1/4.
Yeah, these we got.
-1
-1. Yeah, sorry. We also have to check all of these boundaries. This point, this point, this point, and that point. And that should answer that question. Yeah, we check the same way you check the boundaries of the two-dimensional object, which are these right here. You also have to check the boundaries of those, which are just points. So you just plug the point in. This point, which is the point 1, -1, you have to check that point. You have to check this point, which is the point 1, 1. Yeah, you have to check this point and that point. Plug it in when t is equal to 0. Yeah, over here, in the equation here, you get x squared plus 0, right? What's your x? It's your 2 cosine of t. What's cosine of t when t is equal to 0?
Cosine, 1.
1. Yeah. So it's 2 squared, which is 4.
Oh,
So that's that point. Yeah. To find that, what that point is, you plug it right. What's the point where t is equal to 0? It's that point right there. Right?
domain.
It is the domain, but what's that point over there? Right? That's when t is equal to 0. What's that point? Yep.
You said something about office hours on Zoom.
Yeah, yeah. Just
So-
email me and we'll
Okay.
figure something out because I honestly need to.
Oh,
Sorry.
sorry, can I grab my charger for you?
Yep, sorry.
Thank you.